What's going on, Derek?
Oh, just cleaning my bike. About to go for a ride.
Sweet.
What are you up to?
I'm about to go do my engineering project on dynamics, but I don't really know what to do.
Oh, dynamics?
Yeah.
Wow. Well, just follow me. I have some great ideas.
Sweet.
So you're doing a project on dynamics? Well, I have the perfect topic for you. It has to do with the law of conservation of energy. Basically what it says is that the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. In our case, we're going to be looking at an object rolling down an incline from a height h. And at the top, it's at rest, so the velocity will equal 0, so our kinetic energy equation will equal 0. Bam. Now let's look on the right side. At the right side, the ball has hit 0, so the potential energy equation is now eliminated. Bam. So what we're left with is mgh1 is equal to 1/2 mv squared. But nothing's lamer than rolling balls down a hill, so we'll be using bikes instead.
Well, welcome back. During our experiment, we used a global positioning system to find our elevation change and our final speed. Given these two values and using the law of conservation of energy, we were able to find the potential energy and kinetic energy. Now, if we look at the theoretical values of our potential and kinetic energy, we can see there's an obvious equal relation between them. But if we look at our experiment, that is not the case. There is actually a 9.26% difference in these two values. Now, we could look at the final speed of the theoretical value is 11.96 meters per second. And we got a final speed in our experiment of 11.4. So we were actually going slower than we should have been. Now, why is that happening? Well, if we look over here at our sources of error, there could have been wind resistance and air resistance causing a frictional force direction opposite of our movement, therefore decreasing our velocity. Now, wheels turn based on static friction. But if the wheels slipped for some reason, then there would be a kinetic frictional force in this direction, therefore, again, causing a slower velocity. And this all makes sense when we look at that difference.
Never gonna give you up, never gonna let you down.
In the topic of dynamics, we look at projectile motion, specifically these three equations. The first equation is the final velocity is equal to the initial velocity plus acceleration multiplied by time. The second equation is the final location is equal to the initial location plus initial velocity times time plus 1/2 times the acceleration times time squared. The last equation is the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the location. We will use these equations to find both the final and initial velocities, the angle at which it was thrown, and the max height of the ball. By knowing the distance between the two people and recording the time, we were able to solve for these variables.
Never gonna run around and desert you, never gonna make you.
For the distance the ball has traveled as 18.288 meters and the time the ball traveled as 2.57 seconds, we can solve for the initial velocity in the x direction and the initial velocity in the y direction. It is important to keep the x and y direction components in two different equations. First, we will solve for initial velocity in the x direction using this equation shown. We can plug in the time and the distance traveled when needed. We will get the result that the initial velocity in the x direction is 7.115.95 meters per second. Now we can solve for the initial velocity in the y direction. We will again plug in the variables needed. The time will remain the same in the x and y direction as 2.57 seconds. The acceleration in the y direction will only be caused by gravity, which is 9.81 meters per second squared. As shown in the equation, we can solve for the initial velocity in the y component as 12.60585 meters per second. Now that we have solved for the initial velocities in the x and y directions, we can solve for the magnitude of the velocity using Pythagorean theorem based on a right triangle. We calculated the magnitude of the velocity to be 14.475 meters per second. We can also solve for the angle at which the ball was thrown based on Pythagorean theorem, deriving the equation tan theta is equal to the initial velocity in the y divided by the initial velocity in the x. The angle at which the ball was thrown was 60.5 degrees. We know that the initial velocity in the x is equal to the final velocity in the x because there is no acceleration in the x direction. We also know that the initial velocity in the y is equal to the negative final velocity in the y. The equation shown here will give us the maximum height that the ball traveled. Half the time the ball traveled, it will be at its highest point. We can solve that the maximum height is 8.09926 meters. We can also add on the height of the person throwing the ball.
This application of dynamics, we take in the known distance of 20 yards, which we found to be 18.288 meters, the time it took, which is 2.57 seconds, and the height of each person of 5'9", which is 1.752 meters, and we're able to solve for three separate things. We solved for the velocity magnitude, which is 14.5 meters per second, which in more relatable terms is 32.4 miles per hour. We got the angle in which the ball was thrown, which is 60.6 degrees, and we got the max height of 9.85 meters.